work energy theorem. The whole chapter of work energy and power revolves around this particular topic, work energy theorem. We till now we have seen the concept of work, we have seen the concept of kinetic energy, we have seen what are conservative forces, we have seen potential energy. Now all of this can help us to solve problems in very easier manner in comparison to Newton's laws of motion method, NLM method, or we call it force method. Work energy theorem is like very general theorem, very diversely applied theorem. Let's see what is its general statement. We are not going behind the proof, but we can have a basic intuition about work energy theorem. Consider a particle with its initial velocity vi. Okay, so we will try to understand what is the intuition behind work energy theorem. And let's say on this particle, the sum of all the forces, means the net force, is directed in some random direction. This is your F net direction. Now this F net will have two components. I am assuming this theta, so that I can define a component of F net in this direction as F net cos theta, and a component of F net this direction F net cos theta is called a tangential direction, which is along the velocity, and this F net sin theta is directed in the normal direction to the velocity, so it is called normal component. I may write it as F normal and I may write it as F tangential. So we have two components. One component is along the velocity vector, or it may, and the other component F net sin theta, which is the normal component, is completely perpendicular to the initial velocity. What are these two components going to do with the velocity of the particle? Let's see. So the magnitude of velocity, its rate of change is given by tangential acceleration. We agree, we have seen this in non-uniform circular motions where there is a tangential velocity as well. So what that tangential velocity do is it changes the magnitude of velocity of the particle. So this will be equals to F net cos theta divided by mass of the particle, which I am assuming as m. What this F net sin theta do? We know that the normal acceleration, which is F net sin theta divided by mass m, it is responsible for its change in direction, or we call it normal acceleration. This is equals to v square by r, which is the speed at this moment divided by the radius of curvature, instantaneous radius of curvature. This is your instantaneous radius of curvature. We can clearly see that the component which is along the displacement, that is F net cos theta, it is responsible for the change in speed, or it changes the speed. Whatever changes the speed can change the kinetic energy. The other component of force F net sin theta, it cannot change the speed v, because if we try to find the power of this normal component of force, we will get the power 0, because F net sin theta and v are perpendicular to each other, right? So it cannot result into any change in kinetic energy. We can clearly see here that it can just change its direction because it is normal to the velocity. So if F net cos theta is responsible for all change in kinetic energy, we can write that the work done due to F net cos theta is responsible for change in kinetic energy, or we actually further write it as F net dx dot product as change in kinetic energy. So this is the work done by net force in the direction of displacement, means in the direction of initial velocity. That will result into all the change in kinetic energy, right? We can derive it properly. We can derive it properly. In 3 dimension, we write it as F net dot dr. We can derive it. It's a purely mathematical way. Let's derive it. Derivation. We have to find the work done by the net force on a system. So work done by net force on the system is because of work done by F net dot dr. In general, we are taking. So F net can be written as Fx I cap plus Fy j cap plus Fz k cap dot dx I cap dy j cap dz k cap. After having the dot product, we get Fx dx plus Fy dy plus Fz dz. And distributing the integrals, we get a situation something like this. Here we can write Fx as m dot ax, or we write ax as v dvx by dx. Right? What did I do? I wrote Fx as m into ax, which is vx dvx by dx. Similarly, I will write Fy, similarly I will write Fz. So, integral, okay, I forgot dx, here dx is, yeah, plus m vy dvy by dy dy plus m vz dvz by dz dz. Further solving it, dx dx dy dy dz dz cancel. M is constant for the mass, and vx vy and vz we can integrate them further. So we will get m vx square by 2. Okay. We will put a initial to final limit. I will properly define the limit in a moment. M vy square by 2 initial to final plus m vz square by 2 initial to final. Okay. We can further write it as m common, 1 by 2 also common. We can write vx square plus vy square plus vz square from initial to final. What is this? This is the magnitude of velocity. We call it instantaneous velocity, or magnitude of instantaneous velocity, or magnitude of instantaneous speed. Both are same. So we can write it as half m v square from initial to final, or we can further write it as half m v final square minus v initial square. This will finally result into a expression like half mv final square minus half mv initial square, which is nothing but k final minus k initial. So this is your statement of work energy theorem, that the work done by net force or sum of all the work done by all the forces will result into a total change in kinetic energy k final minus k initial. Let's see some further meanings, some further expressions which you commonly see in your volumes or any standard books. There are many ways it can be written. So let's write it in all the different ways possible. So various forms of work energy theorem. Various forms of work energy theorem. Okay. So what we wrote, work done by all the forces is equals to change in kinetic energy k final minus k initial. We can write it as, in a system of particles. See, till now we have seen very rare cases of system of two particles, right? See, a wedge and a block. Usually we have seen single particle systems, but we are talking in general general terms. Let's say in a system there are more than two particles. Let's say three particles. These three particles may experience a force from outside, may it a gravity or may it some other force possible. Uh, these particles may apply some forces on each other, some forces on each other. These particles may apply some forces on each other. These forces are called internal forces, which these particles are applying on each other. Right? There are three particles in my system, and 1 and 2 are applying forces on each other. 1 and 3 are applying forces on each other. Similarly, 3 and 2 might apply forces on each other. Now, the force mg is not an internal force because it is not existing in a pair. There is no particle in the system which is applying these force mg on particle 3 or on particle 2 or on particle 1. All these masses are different. These mg forces are external forces, and let's say I am observing the system from here, but the system is accelerated as well. So the system is accelerated, pseudo forces will appear in the system. So there will be pseudo forces like this, pseudo forces like this, pseudo forces like this on the system, right? So there are three varieties of forces we have seen in general. There can be work done by internal forces, there can be work done by external forces, and there can be work done by pseudo forces, and that all will be equals change in kinetic energy delta K. Now, for this chapter, we are limited to just one particle system. In one particle system, For a single particle system, there is no concept of internal forces for a point particle or single particle. So the point particle may only experience external force and no internal force. And a single particle system have faced external forces and pseudo forces. There will be no internal forces because there will be a single particle. So the work done by internal forces is completely out of picture. We are left with work done by external forces plus work done by pseudo forces. This is equals to change in kinetic energy, right? If there are the system is the frame is inertial, there is no need to take the work done by pseudo forces. But I am writing in general for a single particle system. This is the statement of work energy theorem. This is one statement. Now this statement is further bifurcated in some ways. So the external forces which are acting on my single particle, let's say this particle, let's say it is on a floor and the particle is going somewhere in this manner. This is muscular force or some external force. This is force mg, and there is a friction force, right? And we are observing this situation from a non-inertial frame. There is acceleration a. So there are many forces which came into picture here. There are some forces like mg, which is gravitational force, which is a conservative force. There are some forces like friction, which is a non-conservative force. This is muscular force, which is also a non-conservative force. And there is a pseudo force in the picture because we are observing it from a non-inertial frame of reference. So there is a pseudo force Ma as well. So this work done by external force include work done by external conservative forces plus work done by external non-conservative forces plus work done by pseudo force. This is equal to change in kinetic energy. Okay. We have also seen work done by external conservative force is always equals to negative change in potential energy plus work done by external non-conservative force plus work done by pseudo force is equals to net change in kinetic energy. So work done by external non-conservative force plus work done by pseudo force is equals to delta K plus delta Q. This sum is called mechanical energy of that single particle, change in mechanical energy of that single particle. So work done by external non-conservative force plus work done by pseudo force. So this is again one more statement which you will see very much. If pseudo forces are not there, you can write this term as 0, and when pseudo forces are not there, work done by pseudo force will be 0. Or let's say pseudo force don't do any work here. Just, then also we can write work done by external non-conservative force is equals to net change in kinetic energy plus potential energy, that is net change in total mechanical energy of the system. Okay. Now, uh, we can see a illustration, a problem where a lot of these forces are involved. Okay, let's see a very intermediate level of problem where I can involve most of the forces for a single particle system. Okay, let's see. This is a hollow sphere. This is a hollow sphere, and inside this hollow sphere, there is a particle. This is your vertical axis. This is your vertical axis. The system is under gravity, and this hollow sphere is accelerating with a constant acceleration. Okay. So the system is accelerating with a constant acceleration a. Initially, the particle is directly below the center of the hollow sphere. The center of the hollow sphere I am assuming as C, and the initial location I will assume as CP. Now, as the hollow sphere will accelerate in forward direction, the small particle of mass m start moving in backward direction. The question is asking up to what maximum angle, up to what maximum angle this particle of mass m will go up. So we have to find this maximum angle theta naught. This is the problem. Up to what maximum angle the particle will reach with respect to the vertical axis. So we have to find that. Okay. Now, let's try to understand the situation. Let's try to understand the forces. So the forces are on the particle of mass m. The forces are mg in downward direction, normal force in upward direction, and since I am an observer, I am an observer inside the hollow sphere. I am choosing it so for convenience. So I am a non-inertial observer now because I am inside the hollow sphere. I am moving with the hollow sphere. So pseudo forces will come. So a single pseudo force of mass into acceleration of the frame, that is A. Ma force is now for me acting on the particle of mass m. You can see this n and mg will balance each other so that the particle stays on the hollow sphere surface in the contact, but this ma will try to push the particle in backward direction. Okay, so initially the velocity of the particle is 0, but its net force is in backward direction, so it will accelerate in backward direction ma. It will go, let's say it has reached somewhere here at an angle theta. We are here to discuss why there should be a maximum angle theta. Okay, let us discuss. At this moment, the force mg will not change. The force ma will also not change. These two forces are constant. The normal will change its direction towards the center of the hollow sphere because of the radius of curvature of this, because of the curvature of the spherical surface on which the mass particle is moving. The normal has changed its direction. If we try to see the components which are balancing the normal, so this particle stays in contact with the surface, the component will be along this line. This angle will be theta, and if I draw a tangent here, this angle will also be theta. Okay, we can see the component, one component of mg in this direction, it can be written as mg cos theta, one component of ma in this direction which can be written as ma sin theta. So ma sin theta plus mg cos theta. I forgot to mention that this hollow sphere has a smooth surface, so there is no friction. Now this ma sin theta plus mg cos theta will try to balance n. They will balance n. So the normal force n will be equals to ma sin theta plus mg cos theta for any theta. Okay, this is not very relevant to our analysis. The other two components which of mg are mg sine theta, and this one of MA is MA cos theta. On this particle, if I remove all the analysis I have done and just see these two components, because every other forces are balanced. This normal is in fact balanced. Now if I see these two forces MA cos theta and MG sin theta, these two forces may or may not be equal at a particular distance. Which force is greater and which force is less? Let's try to understand. MA cos theta and mg sin theta, which force is greater? So initially, because the net of these two forces will apply the force on this particle. So if the particle is initially having net force in this direction, we will ask how much is the net force on this particle in this direction so as to move further upward. If we see this theta is increasing with time, initially this mg sin theta is 0, this ma cos theta is so the tangential force on the particle is actually ma cos theta minus mg sin theta in upward direction, in tangential direction, in this direction. This is the net force. If I try to visualize, as theta will go up, as theta will go up, this mg sin theta will go up from 0 and this ma cos theta will come down. Okay, so there will be a moment when this ma cos theta and mg sin theta will become equal. Ma cos theta will be equals to mg sin theta. That theta is a particular special theta. We will call it equilibrium position later when we will understand it. With the concept of oscillation, we will have this theta as very special status. We will call it equilibrium theta, where the net tangential force on this will be 0 or net forces on the particle of mass m will be 0. Now, at this moment, the forces are balanced and the net force on the particle is 0. Okay, the net tangential force on the particle is 0, but the particle has achieved some velocity till here. Because of this velocity, it will go further upward. It will go further upward. As it will move further upward, what will happen? This theta will further keep on increasing, and this theta sin theta will further keep on increasing, and cos theta will further keep on decreasing. So ft will eventually become negative, or the net force will eventually become in downward direction, which will decrease, keep on decreasing the velocity, and at a moment there will come an instant where the velocity of the particle is 0. We will call this as theta naught, and our purpose is to see these two situations where initial velocity is 0 and the final velocity is also 0. We will apply our work energy theorem between these two situations. I hope we are clear. So now we know that the tangential force is initially in upward direction. It is trying to take the particle up, and at a point the tangential force will become 0. But the velocity is still tangentially upward. So the particle will not stop, it will keep on going until the tangential force, which will become negative after that moment, will try to decrease the velocity, keep on decreasing the velocity, and the velocity becomes 0. The particle at that instant when its velocity becomes 0, we have to find that theta naught. Now, what was the initial situation? Initially, the particle of mass m was here. The forces are in upward normal m, downward mg, and leftward ma. The direction of this mg, ma and ma are constant. Okay. These two are constant forces first of all, and let's say this is your maximum angle theta naught. At this moment the velocity of particle is final velocity is 0. Initially the velocity of the particle is also 0. Let's apply work energy theorem in this statement. So what is the statement of work energy theorem? Work done by all the forces is equals to change in kinetic energy. What is the work done? Work done by normal force, work done by gravity plus work done by pseudo force is equals to change in kinetic energy. Okay. So this work done by normal force, we know that since at every instant the normal is perpendicular to the displacement vector, we will call the work done by normal force directly equals to 0. Work done by gravity, for the work done by gravity, we will say the work done by gravity is actually how much vertical height it has traveled upward or downward. So work done by gravity is given as mgh. If h is the height it has traveled against the gravity, the work done is minus mgh. So we will write the work done by gravity as mg minus h. How much is this height h we can find actually? Let's assume this radius of the solid sphere, the hollow sphere is r. This component of r will be r cos theta naught. We can easily write h as r minus r cos theta naught, r being the whole distance and r cos theta being this distance. Okay, so we found this h from the initial vertical position to final vertical position where the particle will be. So how much is h? H is r minus r cos theta naught plus work done by pseudo force means work done by ma. Work done by ma, which is a constant force, will be equals to the force into displacement in the direction of force, which is this displacement. How much is this displacement? This displacement is r sin theta naught. So we can write work done by pseudo force as ma into r sin theta naught. Since ma and r sin theta naught both are in leftward directions, the work done is positive and equals to what is the net change in kinetic energy? Since initial speed is 0, final speed is also 0. So the net change in kinetic energy is 0 because kinetic energy is half m speed squared. We have to solve this for theta naught to get the theta naught. So we will get MAR sin theta naught is equals to MGR 1 minus cos theta naught. MR cancel. We have sin theta naught as 2 sin theta naught by 2 cos theta naught by 2 by our trigonometric identity, and 1 minus cos theta naught we can write as 2 sin square theta naught by 2. 2, 2 cancel, sin theta naught by 2, sin theta naught by 2 cancel. We have a by g as tan theta naught by 2. We can further write it as theta naught by 2 is equals to tan inverse a by g, or theta naught is equals to 2 times tan inverse a by g. So at this maximum theta naught, the particle will climb up on the hollow sphere, and after that what will happen is called the concept of oscillation. So that is a really interesting problem. Although we have reached to the solution of the problem, this is the solution. Theta naught is equals to 2 tan inverse a by g. So let's see what will happen further to this system. Since it is interesting, we would love to discuss it. I am erasing it. Okay. So, further to this, what will happen to our particle? We saw that the particle was at lowermost point m, and at this point, the net tangential force on the particle was ma in this direction. When the particle did reach its maximum theta naught, the net tangential force on the particle was how much? Can we find the net tangential force at this theta naught? Of course, we can find. Our theta naught is 2 times tan inverse A by G, right? So, since at this moment the tangential forces must be mg sine theta and ma, uh, wait, this is, yeah, correct, yeah, this is ma cos theta. At this moment they are theta naught. Since we have crossed that position which we called equilibrium position for a moment, I will denote it as theta 1, okay, or I will denote it as theta equilibrium. Why equilibrium? Because at this moment the net tangential force on the particle balanced. So at theta equilibrium, what happens is this mg sine theta equilibrium is equals to ma cos theta equilibrium. So what was this angle? This angle was actually tan theta equilibrium is equals to a by g. So theta equilibrium is equals to tan inverse a by g. It's not a coincidence that this theta equilibrium is half of this theta naught, or theta naught is double of this theta equilibrium. It's not an incidence at all. When we will study oscillations, we will see that this is your equilibrium position, this is your one extreme, and this is your another extreme. When the particle will go up, reach here, this ma cos theta naught is much less than mg sin theta naught, and at this point the velocity is 0, so the particle will come downward. The particle will come downward, and it will reach back here. When it will reach back here, its velocity will again become 0 because of the conservation of energy, right? So, if its speed is again 0, since net ma is in this direction, it will again come back and it will again pass through this equilibrium position. So, it will keep on oscillating between these two positions, right? So, from equilibrium, the distance of this extreme position, angular distance of this extreme position is equal to the angular distance of this extreme position. So, we can easily write theta naught as 2 times theta equilibrium, that is 2 times tan inverse A by G. So, what will happen to the particle? The particle will keep on oscillating like this in between these two positions, right? So, that's it for today, guys. This is one more.